So hello everyone, my name is Pratik Piyush, roll number 220103083, and this is my submission for assignment 1 of our course DA 623 Computing with Signals. And my topic of interest which I am presenting to you here is polynomial regression, underfitting and overfitting, both the cases are covered. So first we will describe a problem set that we want to tackle, because if we want to understand it clearly we'll have to solve a problem and see how it goes. So we are taking the temperature data and then we are going to use polynomial regression, and then we will study the underfitting and overfitting cases in this. So just a little brush up of all the mathematics that is going to be involved. Firstly we'll see that this is the formula for polynomial regression, which has k degrees, and we'll define error on each data point, which we will say as our loss function. Not exactly our loss function, but this is what we define as the error, and this will be our total error for all the points. This will be our cost function. And one other way to represent this in matrix form is this as well. So yeah, these are all the mathematical backgrounds that we need as of now. So let us jump to the main topic. And yeah, so before that I would like to make a synthetic data with additional noises, so that our model will not be able to capture the equivalent equation for this. So as we can see, this is a sine wave going like this, and we have some additional noises. Basically we have taken the mean temperature to be 25 with a 5 amplitude of sine function and some error, so that we can clearly see what patterns the underfitting ignores, or the overfitting takes too much, or the moderately fitted model ignores. So let us move to the next slide of our presentation, which is underfitting versus overfitting. So basically, to fit this, we do not know that this is a sine equation or not, because since we are solving it for the first time, we will see this as a normal data set, and for the machine it is just a bunch of points, a bunch of numbers. And since we have decided to solve it through polynomial regression, we'll see that the degree of the polynomial has too much effect on how our model will perform. Like for example, as you can see, for the degree 1, it is just going to be this line, which is basically, it will kind of take the mean, and this will be the mean line. That this will be no, it won't be the mean line exactly, but it will be just a polynomial of linear form, which will not capture the curves that are there in our data set. And slowly we increase it. For example, we have taken here degree 1, degree 3, degree 9, degree 15. So for degree 3, as we can see, the polynomial has tried to capture it clearly, but it has not captured everything. And degree 9 does capture some things clearly, but as we can see, all degree 3 to degree 15, they all form the same shape, so they are capturing the trend or the curvature that is present inside our data set. And here but there is a minute difference in that. So in degree 3, as you can see, the curve is more smoother throughout the data set. But in case of a degree of 9, it is deviating a little bit if the points are a little too far. If there is some noise, then it is getting affected, but it is not getting affected that much. Whereas for overfitting, which is the highest degree of polynomial, which is degree 15, not the highest possible, but like the ones we have taken, it tries to fit through the points in a very sleek fashion. It is going from every point to point, and this is the problem with overfitting. So now if we have any test data set, or if we want to test our model on some real life data set or anything, then it will only predict according to this model, and it will not take consideration of the other states. So the error will increase in the testing, but the error here, as we'll see in the next slide, is very low. So let us move on to the next slide, which is this. Training error as a function of model complexity. The complexity of model here is defined as the degree of polynomial that we have. So see, I have taken from degree 1 to degree 20, and you can see that in degree 1 the error is a lot. This portion is way higher, and this is the adequate portion in which we want our answer to be, because this is all overfitting cases. All these are overfitting cases because they are just trying to capture what the training data set has, and just to that. So they will be very perfect on the training they will be very perfect on the training data set, but they won't be as good as they perform in the train, but they will not perform good in the test, as we can see. So yes, with the increasing degrees, the risk of overfitting increases, and if it is too less, then it will be underfitted. So it won't capture anything, it won't capture the essence of the data or the relation the data set is following. Let's move on to the next slide now. So right, the conclusions is low degree creates underfitting, high degree creates overfitting. Low degree is high bias, or you can say moderate bias, because it does not capture the relationship of the data set, and it might be very bad for test, but sometimes it might be good. So that is why the bias can be from moderate to high range. But if it is high degree and overfitting case, then variance is very high. We define variance as the change of how model predicts or how it works on the test and training data set. If the variance is high, that means the training is very good and the error is very less, but in test it is varying too much. So yes, thank you so much, and I will now continue with the coding part. So yeah, thank you so much for watching the presentation. Hello everyone, this is the code that I was talking about. So as we can see, I have already run the code once, but here I'll run it again. So first of all, we'll be taking NumPy and PyPlot, Matplotlib for the graphical representation, and our mathematics convenience, we are taking NumPy. So yes, first we'll take a random seed as 0 so that we generate the same data every time with the noise included, because every time the noise can change. So just for reference, we have taken seed is equals to 0, and first we define the linear space and then we define the noise, and here is the equation, and then we have plotted it. But in particular this is a scatter plot that we are seeing here. So yeah, let's jump to the next portion. Let me just first run this code as well. So yeah, here is it, and then we have just tried it for some different polynomials to see how the overfitting is done, or the underfitting is there, or what is the perfect fit. So we have plotted just 1, 3, 9 and 15 here, and yeah, as we can see, these are the results of that. Yes, here they are. And now let's move on to the next section of our code, where we calculated the error. How much does every degree of polynomial shows in the polynomial regression, and here we can see, let us run this again, and yeah, here is the plot. So the initial portions have very high error, then we find the best one, and then here are all the underfitting degrees of polynomials. So yes, that was my code. Thank you so much for watching.